This is lesson 99, Uniform Motion, Unequal Distances. This is Saxon 3rd edition, Algebra 1. Now, we've dealt with motion and distance problems in a couple of lessons now. In lesson 92, we dealt with equal distances. So, distance of one thing equaled the distance of another, and that was the formula or the equation that we used. In lesson 94, we had the distance of one thing plus something else then equaled the distance of the second thing. In this lesson, we're going to do have a new equation. So some uniform motion problems tell us that one person or object traveled a greater distance by a certain amount or a specified amount than the distance traveled by another person or object. So when this is the case, and hint, hint, when you see little 99 in parentheses under the problem number, you're going to know that this is the type equation that I'm going to use. So basically, the distance of the first plus some specified amount is going to be equal to the distance of the second. And since we know that rate times time equals distance, what we're going to use to substitute in is rate of the first time of the first plus this specified amount is going to equal the rate of the second time of the second. So let's go ahead and do some examples, and then we'll do 2 practice problems. Example 1 says at 8 p.m. Achilles left camp and headed south at 20 kilometers per hour. At 10 p.m., now this is 2 hours later, right? Patroclus headed south from the same camp. If Patroclus was 50 kilometers ahead by 3 a.m., what was his speed? And we know that speed means rate, so we're looking for the rate of Patroclus. All right, so our equation, or our diagram of the equation, is going to be like this. Achilles leaves, and Patroclus leaves 2 hours later, but he is 50 kilometers ahead. So he somewhere here he gets ahead. They were equal up to this point, and then Patroclus pulls out ahead. So they could not have had the same speed for him to do that. All right, so we're going to set it up. The distance of Achilles plus 50, the amount that Patroclus got ahead, is the distance of Patroclus. And then we're going to change distance to rate times time, and then set up the very same equation. Then we're going to start pulling out what can we substitute in. What do we know? We know that the time of Achilles, because he left at 8 p.m. and then we're going until 3 a.m., that is a total of 7 hours. And Patroclus didn't leave until 10 p.m., so 2 hours later. So his would be 7 minus 2, which is 5. The only other thing that we know is that Achilles' rate is 20 kilometers per hour. So that's good. We know 3 things we can substitute in, and we can find the 4th thing, which is the rate of Patroclus. All right, so rate of Achilles is 20, time of Achilles is 7, plus 50 is equal to 5 RP, rate of Patroclus. We add our like terms now, 140, 20 times 7 is 140, plus 50. We get 190 equals 5 RP. And then to get RP alone, isolated, we divide both sides by 5. When we do that, we find that Patroclus' rate is 38 kilometers per hour. So you've got Achilles going at 20 miles per hour, and Patroclus almost double that at 38 kilometers per hour. Example 2 says Rachel has a 15-kilometer head start on Charlene. How long, now we're going to be looking for time in this one, how long will it take Charlene to catch Rachel if Rachel travels at 70 kilometers per hour and Charlene travels at 100 kilometers per hour. All right, so this 15 here represents the head start that Rachel has on Charlene. She has already gone 15 before Charlene ever even starts. So we can set this diagram up to look like this. 15 plus the distance of Rachel equals the distance of Charlene. And then we change it to our rate times time equation. Then we're going to pull out what do we know. It tells us Rachel's rate, which is 70, and Charlene's rate is 100. And we know that the rate of Rachel, the time of Rachel is going to be equal to the time of Charlene because time starts here and ends here. Okay, so they had same amount of time. So when I substitute into my equation, I'm going to be looking for Charlene's time. So I'm going to substitute in here for TR, time of Rachel, I'm going to substitute in TR is equal to TC. So I can say 15 plus 70 TC is equal to 100 TC. And then I'm going to move this 70 TC to the other side so I can get those like terms alike and together. And when I do that, I see that 15 is alone here and 100 minus 70 is 30 TC. When I divide both sides by 30 to get TC isolated, I'm going to see that 15 over 30 is the same as 1/2. So it's going to take Charlene 1/2 hour to catch up to Rachel because she's going 30 kilometers per hour faster. In example 3, Harry and Jeanette jog around a circular track that is 210 meters long. Jeanette's rate is 230 meters per minute, while Harry's rate is only 200 meters per minute. So Jeanette is going faster than Henry. In how many minutes, again we're looking at time, will Jeanette be a full lap ahead? All right, if she's a full lap ahead, they're not going to have an equal distance. Harry's, we're going to have to add 210 because it's 210 meters long. And to get one lap, she'd have to go all the way around. So Harry's distance plus another 210 is going to be equal to Jeanette's distance. So we do our rate times time formula or equation. And we're going to substitute in right here, TH is equal to TJ, so I'm going to substitute TH in here for this TJ. And I have 200 TH plus 210 equals 230 TH. Now I need to get all my TH's on one side, so I'll subtract 200 from both sides. When I do, I'm left with 210 equals 30 TH. Now I want to get TH alone, so I'll divide 30 by 30, and I'll have to divide 210 by 30, and that gives me 7. So Harry's time is going to be 7 minutes it's going to take for Harry, to catch up with Jeanette, who is faster. All right, let's work our practice problems. At 5 a.m., Napoleon headed south from Waterloo at 4 kilometers per hour. At 7 a.m., Wellington headed south from Waterloo, same starting point. If Wellington passed Napoleon and was 20 kilometers ahead at 2 p.m., how fast was Wellington traveling? So we're going to be looking for Wellington's rate, the rate of Wellington. I've taken this diagram where I drew it and I've turned it into our rate times time equation for this type of problem. and I see that I'm going to need to pull out what I've got. We know that Napoleon's rate is 4. What do we know about time? Well, Napoleon's time, he left at 5 a.m. and then traveled until 2 p.m., which is a total of 9 hours. And then Wellington didn't leave until 7, so the time of Wellington would be 2 hours less than this, or 7. Now I'm going to start substituting in. And then I'm going to do the math. 4 times 9 is 36, and 36 plus 20 is 56, equals 7 RW. If I divide both sides by 7, I'm going to see that 8 is Wellington's rate. Okay, let's do the next one. Alright, this one says that Helen has a 4-kilometer head start on Paris. How long, which is time, will it take Paris to catch Helen if Helen travels at 6 kilometers per hour and Paris travels at 8 kilometers per hour? Alright, so Helen here has a 4-kilometer head start on Paris. Alright, so we give her the 4, and then she's going to go the rest of the way. Paris she doesn't get given anything. She's going to have to go the entire thing in her amount of time. So what do we know that we can fill in? Helen's rate of Helen is 6. The rate of Paris is 8. And what can we know about the time? Well, they're the same. Time of Helen is equal to the time of Paris. Okay, so let's set up our equation. RHTH plus 4 equals RPTP. And we'll substitute in 6 here and 8 here. And TH is equal to TP, so right here I can put TP in and just be solving for TP. So now I have 6 TP plus 4 equals 8 TP. And I need to get my TPs all on the same side. So I'm going to move this 6 to the other side. When I do, that cancels out. I'm left with 4 is equal to 2 TP. When I divide by 2 on both sides, I'm going to find that it's going to take Paris 2 hours to catch Helen. Alright, good job, and I'll see you next time for lesson 100.